more on equilibrium distribution. Remember that we are talking about solubility of a gas in a liquid. Okay? So from previous subsections, we saw phase diagrams, and we saw not only how vapor liquid distribute, but also how solubility might distribute here. In this specific case, I have two cases. X-axis, which is the mole fraction of the solute, which is the gas. Here, let it be A, in liquid. So let it be liquid, solute A in liquid, let it be the liquid water. And then I have y-axis, which is here, mole fraction of solute A in the vapor, which technically should be a gas, but right now remember that you may even encounter these as interchangeably, which is not always correct, but for the sake of this demonstration, let it be true. And y, let it be this air. Actually, let's assume that this is the ammonia case we were watching before. Ammonia can be in air or water. And as you can imagine, if we were to fix this at given pressure and temperature, so this is very interesting comparing versus the distillation, that we need to fix pressure and temperature to draw a single line. So if I were to change the temperature, most likely you will change the distribution curve. So try to imagine what will happen if I decrease temperature. Typically, if I decrease temperature, gases become less or more soluble. Try to guess that. And if so, how will it shift? Should it shift to the left or to the right? Remember that X stands for the liquid, Y for the vapor. Anyways, what I wanted to show you is that this is fixed at a pressure and temperature. Now, interestingly, you will see that there are many diagrams at 1 atmosphere, but if you were to operate at different pressures, well, those equilibrium curves are kind of hard to get. Sometimes you should do them by yourself, or research them, or even assume some cases. The gas absorption process involves the red distribution of solute between the gas phase and the liquid phase, of course. And it here doesn't make sense if you were to say, okay, what's in this point? There is no gas, no liquid. No gas, no liquid. Why? Because there's only one point in which you could have the equilibrium line at the given pressure and temperature. So this doesn't make that much sense. Okay? So just for you to know. What will happen if you were actually having this point right here? Well, that is the operation point, and you will see that there is a, let's say, driving force between the equilibrium and that point. We will see that later. The equilibrium distribution curve is the relationship between the solute concentration in the gas phase and the liquid phase at constant pressure and temperature. I'm repeating this because it's very super important. Note that not the same for distillation and absorption. So in absorption, you have, let's say, an equilibrium line, and you have, I don't know, vapor here, liquid here, and the vapor-liquid condition here. Well, in this case, this doesn't make that much sense. There is no equilibrium here. In distillation, we have seen that the equilibrium curve simply shows the equilibrium between two components, the more volatile and the less volatile. For instance, water and ethanol. Typically, we're talking about T-XY diagram. At high temperatures, let's say high pressures, you will have water, and low pressures you will have the ethanol. The points represent vapor-liquid equilibrium. So yeah, remember this will be a vapor-liquid equilibrium in the liquid phase and in the vapor phase. The solubility curve can lie anywhere in the XY plot by definition. But in gas absorption, remember we're talking about gas-liquid, this will be vapor-liquid operations. As noted in the previous section or slideshows, the simple case will be 3 components, so that's very important. Before we had 2 components, water and ethanol, and now we have the solute, air. Well, technically air is not a component, it's a mixture, but let's assume this is okay. Or for simplicity, let's assume this is just nitrogen phase. The gas phase and water. So by definition, you should have at least 3, because you should have a gas, which is acting as a solvent, a liquid, which is acting as a solvent, and a smaller gas, which is acting as a solute, and a smaller gas, or the same gas, that goes into the liquid phase. The equilibrium solubility curve is plotted for a particular constant temperature. Any point on the same curve represents gas solubility at the same temperature. So this is interesting. This is the same temperature at this point. This point has the same pressure at this point. Okay, let's check out some examples so we have a clear vision of what we're talking about.